Good afternoon, students. So last class we have seen about the interrupt special function register, that is interrupt enable register and interrupt priority register. Also we have discussed about external hardware interrupts, and hardware interrupts activation can be done by edge triggered interrupt and low level triggered interrupt. Okay. So here the external interrupt activation can be done by two signals, that is edge triggering signals and level triggering signal. So when the edge triggered is selected means, okay, when edge triggered is selected, only interrupt is activated when high to low transition is detected on interrupt pin. So as soon as high to low transition is detected, the interrupt signal is sent and 8051 executes your interrupt service routine. That is the concept behind edge triggered signal. Okay, so your device 8051 will recognize the interrupt at the edge of the clock pulse. So we have two external hardware pins, E3.2 and 3.3. So 3.2 is called it as INT0, external interrupt 0. 3.3 called as external interrupt 1, INT1. Okay. Suppose when the level trigger is selected, only the interrupt is activated when the signal low level is present. When the signal is low, your interrupt signal is recognized by 8051. And it is possible that the ISR may be called many times as long as this signal stays low. So that is the difference between edge triggering and level triggering. So the important point is here. So the default mode, that is upon reset, your 8051, that is your 8051 accepts only level trigger. So normally your INT0 and INT1 are normally high. Okay. So these two are active low signal. So this signal should be activated when the particular pin receives low signal. So that is the meaning. Okay. So active low means the signal is low, the signal is activated. If it is high, the signal is not activated. So that is the meaning. So these two are normally high, and level triggered is default mode upon reset of 8051. So the default mode is level triggered. So by default, it is in logic 1. When the signal is detected, at the level, it will recognize the interrupt signal. So this is the diagram for level triggered signal. Suppose if you want to configure the microcontroller to accept edge triggered signal, you have to configure this IT0 and IT1 set to 1. To configure your microcontroller to accept edge triggered signal, we have to make this IT0 and IT1 is equal to 1 in TCON register. So this register is TCON. When IT0 and IT1 is equal to 1 means your 8051 will accept edge triggered signal. If it is 0 means it's a default mode, it will accept level triggered signal. Is that clear? So we have two flags associated with your external interrupts, IE0 and IE1. IE0 is the H flag for interrupt 0, IE1 is the H flag for interrupt 1. Okay. So when the external signal detected on INT1, which means that the high to low pulses detected at P 3.3, okay, when the signal is detected means this IE naught is going to be 1, otherwise 0. Similarly, here IE1, the high to low pulses detected at P 3.2, this IE1 is equal to 1. Okay. So generally IT0 and IT1 bits set low level or edge triggering mode of the external hardware interrupts of INT0 and INT1 pins. So there are both 0 upon reset. Okay, IT0 and IT1 are 0 upon reset, which makes them low level triggered signal. So here, in case of IE not external interrupt edge flag, set by CPU when external interrupt signal is detected, cleared by CPU when ISR is executed. That is when return I instruction is executed and does not latch low level triggered signal. It will not accept low level triggered signal. So the control, the edge triggering and level triggering can be done by using this IT0 and IT1 in TCON register. When IT is equal to 1 means your 8051 will accept edge triggered signal, otherwise level triggered signal. So this is the internal block diagram of accepting external interrupts. So here IT0 and IT1. So edge triggering and level triggering can be selected by using this IT0 and IT1. When IT0 is equal to 0 means the signal is edge triggered signal. Your 8051 accepts only edge triggered signal. Okay. So that signal is inverted and given to your 8051. So based on the interrupt signal, your 8051 will service the interrupt request. Suppose if your IT0 is equal to 1 means here that signal is the edge triggered signal. So these bits, that is your IE1 and IE0, okay. So these bits used by 8051 to keep track of edge triggering interrupt only. So IT0 and IE0 and IE1. So these bits used by 8051 to keep track of the edge triggering interrupts only. So in other words, if IT0 and IT1 are 0 means that the hardware interrupts are low level triggered. Okay. So that case, when the signal is low level triggered, signal means this IE0 and IE1 are not used at all. Okay. This is IE0 and this is IE1. If IT0 and IT1 is equal to 0 means your hardware interrupts are low level triggered signal. Okay. So these two flags are not used at all. Okay. So these two flags are used internally by 8051. So the programmer or user is not concerned with these bits since only for internal use. So microcontroller and set or reset this IE1 and IE0. Okay. So upon edge triggered signal, INT0 and INT1, the 8051 set IE0 and IE1 in TCON register. So only execution of return I instruction at the end of the ISR will clear IEX register, IEX bit. So the level triggering and edge triggering can be done by using IT0 and IT1. If it is 0 means the signal is a level triggered signal. So that signal is inverted in order to activate your external interrupt signal. So it will interrupt your 8051 and your ISR will be executed. Suppose if it is edge triggered means that is IT0 is equal to 1 means the signal is edge triggered signal. So this flag is set to 1 to indicate that your 8051 will accept only edge triggered signal. So based on that request, your 8051 will get interrupted and ISR will be executed. So this is the logic diagram behind your external interrupts. Okay. Any doubts regarding external interrupts? So the level triggering and edge triggering will be decided by IT0 and IT1. IT0 and IT1 is equal to 0 means your 8051 will accept only level triggered signal. Suppose these two bits are 1 means your 8051 will accept edge triggered signal. Any doubts regarding this? So upon edge triggered pulse, IT0, that is upon edge triggered pulse on IT0 and IT1, your 8051 set IE bit in TCON register, that is IE0 and IE1. So after the execution of return I instruction, that IEX is cleared. Any doubts regarding this? Yes or no? So can you identify the difference between level triggering and edge triggering? Students? Students, is that clear? Any doubts regarding this? What about others? Okay. So this is the overall interrupt structure of your 8051 interrupt. That is the overall interrupt structure of your 8051 microcontroller. So here we have two important register, IE register and IP register. In IE register, we have two level of control. So the first level of control will control each individual interrupt request. Okay. So two level of control. First level is the basic level, that is the individual interrupt level. And this is done by 5 interrupt flags. Okay. What are the interrupt flags? Please tell me. How many interrupt flags available in IE register? How many flags available in IE register? How many interrupt sources in 8051? Please tell me, what is the content of IE register? So your IE register holds how many flags are available in IE register? Please tell me. Otherwise I can't proceed. Huh? How many flags are available? Five. So what are they? E serial interrupt, external interrupt 0, external interrupt 1, timer interrupt 0, timer interrupt 1. Okay. So we have two level of control here. One is individual interrupt control. So this is done by your 5, that is the control is done by 5 interrupt flags in IE register. And another control is a global control. So that is done by EA. So EA, we have one switch, and this switch is for your interrupt sources, 5 interrupt sources, individual interrupt sources. So this first switch is the global enable, okay, and second one is the individual interrupt control. And already I have explained this INT0 and INT1. So your edge triggering and level triggering can be selected by using IT0 and IT1. When IT0 is equal to 0 means your 8051 accepts level triggered signal, otherwise edge triggered signal. If it is edge triggered signal, the flag will be updated. That is IE0 and IE1 will be updated. And here, based on the interrupt request, next step will be the interrupt priority. So it will determine the priority for individual interrupt source based on the priority and based on the interrupt polling scheme. Your 8051 will service the interrupt. So low priority interrupts, that is your low priority interrupts cannot be pre-emitted by high priority. So high priority can be pre-emitted low priority interrupts. Okay. So that's all about your external interrupts. So next, timer interrupts. So we have two timer flags, that is TF0 and TF1. Okay. So this timer flag set by the hardware to indicate that overflow occurred. Okay. So these flags not to interrupt the microcontroller directly. Okay. It's not to interrupt the microcontroller directly. So microcontroller will be interrupted if ET0 is equal to 1 and EA is equal to 1. So these two bits are available in E register, and next one your TF0 is equal to 1. So in order to enable this timer 0 interrupt, these three bits are set to 1. Otherwise, the particular timer interrupt will not be executed by your 8051. Okay. So these flags, that is TF0 and TF1, not to interrupt the microcontroller directly. The condition is here. First EA must be 1, ET0 must be 1, and TF0 must be 1. These three bits must be 1 in order to enable your timer 0 interrupt. Similarly, timer 1. Okay. Here EA should be 1, ET1 should be 1, and TF1 should be 1. So when three bits are 1 means this interrupt is accepted by the microcontroller based on the priority, or 8051 will service the interrupt request. Okay. And next, serial communication, we have two interrupts. So these two interrupts are together. Either it will accept receive interrupt or transmit interrupt. I will explain this serial interrupts in serial communication topic. Okay. So RA is receive interrupt, TA is the transmit interrupt. Okay. So this is the overall interrupt structure of your 8051. So next we will see how to write interrupt service routine in square wave generation. So this is a write a program to generate a square wave a 50 Hertz frequency on pin P1.2 using an interrupt for timer 0. And your external oscillator frequency 11.0592. Okay. So initially your program code starts at 0. ORG 0. Next, jump to main program. So your main will be stored here. Okay. Based on the interrupt request, your program control is transferred from main to ISR. So every interrupt is associated with one vector address. In that address, we have to store the ISR. And ISR is terminated with return I instruction. When these instructions get executed, based on this return I instruction, your program control return back to main. So this is the concept involved in interrupt service routine in 8051. So here in the given example, we have to generate 50 Hertz square wave on pin 1.2. Okay. So use timer 0 in mode 1. Find out the value of 50 Hertz. Please find out. Hertz square wave. select mode 1 and calculate. So the value is DC00, okay. And here we have to enable your timer 0 interrupt. So first you have to calculate the initial value of the timer based on square wave frequency, and second you have to calculate the IE register content. After that you have to start the timer, okay. So first you have to identify the T mod value. So the mode selection is mode 1. So you have to load the 0, 1 into T mod, okay. And next you have to load the initial value of the timer, that is DC00. So DC should be loaded into higher order register and 00 should be loaded into lower order register. Next we have to find the value of IE register. So here we are going to enable timer 0. So for that, first global bit must be 1, remaining all 3 will be 0, and next 0, 1, 0, 0, 0, 1, 0. So this 1 is representing your ET naught. So to enable this timer 0 interrupt, what are the bits are going to be 1? So the bits going to be 1 is ET naught is equal to 1, EA must be 1, and next TF1 is equal to 1. So these 3 bits must be 1 to enable this timer 0 interrupt, okay. So first load your T mod value, next load your initial value, and next find out the value of IE register in order to enable your timer 0 interrupt and start the timer, okay. So according up to this instruction, your ET naught 1 and EA is equal to 1, your microcontroller is continuously monitoring your overflow flag, okay. So the initial value is already loaded, your timer gets started, start counting the clock pulses. After reaching the maximum value, your overflow flag is set to 1. Your TF naught is equal to 1. So that time your interrupt will be triggered, okay. So your program control is transferred from main to this ISR. So in ISR, what is the application given here? We have to complement your P1.2 for 50 Hertz frequency generation, okay. So complement P1.2, okay. And again you have to load the timer in order to repeat the operation. So you have to store these 3 instructions in which address 000B. 000B is nothing but the starting address of your timer 0 ISR. And you have to store your main program in 0030, and you have to store your ISR in 000B. Okay. So once the overflow flag is set, means your interrupt is triggered. It will interrupt your 8051 instruction execution. So your 8051 stops its current execution and program control is transferred to 000B, and processor start executing instructions stored in 00B. Here, 1.2 is complemented, so square wave will be continuously generated. Is that clear? Any doubts regarding this? So first you have to define your program memory starting address, and after that you have to jump into your main program. Main, initialize your T mod value based on your mode selection and load your timer initial values and define your IE register based on the interrupt request, and after that you start the timer. So once the overflow flag is set to 1, your program, that is 8051, will be interrupted. Your program control is transferred from main to ISR. So the timer 0 interrupt starting address of vector is 000B. So we have to store the instruction in 000B. Okay. Here I am complementing P1.2 and again loading the initial value in order to repeat the process. Any doubts? Students, any doubts? So every interrupt request is associated with one address. So you have to store your address, the corresponding the starting address of ISR, that is corresponding interrupt source starting vector address 0003 000B for interrupt 1 0013, timer 1 001B, and serial 0023, and your main program should be stored at 0030. Is that clear? Yes or no? Students, please reply. Yes. So let's execute this code in KEIL microvision. So here you can see the complete interrupt system of 8051. That is P3.2, the starting address of ISR 0003. Okay, and timer 0B 3.313 1B, and serial receive and transmit have same address 0023. Here we have control signal, that is EA enable access, IT not for edge triggering and level triggering, and IE not for keep tracking of your edge triggered signal, that is INT 0 signal, and EX not is for external interrupt 0. So here you can find the entire interrupt system of your 8051. So here, so based on the clock pulse, your timer gets started. So it is operating in 16-bit timer mode. Once the overflow flag is set, your program control goes to this ISR, particular ISR. Here, we are complementing your P1.2. So square wave is being generated at P1.2 continuously. So when we simulate this in Proteus, so this is a counter timer device. You have to connect this, connect the clock of this particular device to your port P1.2. Here I have connected CRO at P1.2. Let's run this code. So here you can see the square wave is continuously generated at P1.2. At the same time, the timer, that is this counter timer virtual device, is measuring the frequency. The frequency is around 50 to 55, approximately 50 to 55. The frequency of square wave is being displayed in VSM counter timer device. Okay. So next example, you write application, that is write a code for this particular application. Assume that P3.3 is connected to pulse generator, that is your INT1. 3.3 is nothing but INT1 that is connected to one switch or pulse generator. So write a program in which the falling edge, here you have to set your IT 1 is equal to 1. So with the falling edge of the pulse will send height to T1.3, which is connected to LED or buzzer. Okay, so in other words, the LED is turned on and off at the same rates as the pulses are applied to INT1. So write a code for this application. So first you find out the IE register value to enable your external interrupt 1. To enable external interrupt 1, find the value of IE, load that value into IE. So can anyone explain the logic? So what is the value of IE? 1000 0100, not again 100. To enable external interrupt 1, 0100, that is 84. Please check Bala Meenakshi. Not 88, it is 84. EX1 is the third bit. Okay. So 1, 0, 0, 0. Your ET0 is ET1 is 0 and EX1 1, ET0 0 and EX0 0. So 1 0 0 0 0 1 0 0. Move IE, 84. So in main program, you have to initialize this IE register value. That is, load that value into IE register. That's all about your main. And write your ISR. So in ISR, what are the instructions to be added? Data. So explain the logic of ISR. Shweta, are you there? Aarti. Aarti. Aarti is here. Okay. So what instruction should be included in ISR? Please tell me. என்ன பண்ணணும் ISRல? சொல்லுங்க. ஏதாவது ஆன்சர் பண்ணாதான் I can proceed. Set bit P 1.3. Next. So you have to generate square wave. Set bit. What is the next instruction? See, first you have to set this IT1 for accepting edge triggered signal or negative edge of INT1. Okay, so set bit IT1 and initialize your IE register. Okay, so that's two instruction should be included in the main program. Okay, when the interrupt is triggered, that is your P 3 point, that is INT1 is 3.23, I think so. So suppose that pin is triggered means your program control is transferred from main to subroutine. In subroutine, we are generating the square wave with some delay. Set bit P1.3, move R0, 200 and decrement jump no 0. These two instruction will generate some amount of delay. After that, I am clearing P1.3. Okay, is that clear? So once the interrupt is triggered on port 3, this ISR will be executed, and based on the instruction, the square wave is continuously generated at P1.3. So here you can see this is your main program. So you have to set the IT1 to accept edge triggered signal and move your value, that is 84 to IE register. Once the interrupt is triggered, your program control is transferred to ISR. Here this ISR will generate square wave on P1.3. Set bit P1.3 and clear P1.3. In between we have a delay routine. That is move R0, 200 and continuously decrement the R0 value. Let's run this code. Zero, 1, 2. See, 3.3 is your external interrupt 1. I am going to trigger this P3.3. If it is triggered, your program control, so look at this cursor. Okay. Look at this cursor. Your program control is continuously transferred between main and the subroutine, interrupt service routine. So square wave is based on the interrupt signal. The square wave is generated at P 1.3, 1.2. So here in Proteus, you have to connect external switch to P 3.3 to trigger the external interrupt signal. Okay, and LED is connected to P 1.2. So here, when I press this switch, okay, the interrupt is triggered. So the LED is continuously toggling. That is, square wave is being generated on P 1.2. So here you can see the square wave. So based on the input of 3.3, the square wave generation happened. Here, if it is not pressed, your interrupt is not triggered. So your output of this P 1.2 is equal to 0. If it is pressed, interrupt is generated. So square wave is generated at P 1.2. So that's all about your interrupt programming. Yes, Balamina. 1 second. Yes. Tell me.
In the main program, they are
Yes.
assuming IT1 as the input, right? By fixing set B.
IB?
IT1 is required as an input here, say by entering a
Actually,
state B.
we have to set IT1 is equal to 1. Okay.
Yes,
For accepting edge triggered signal. So
yes, ma'am.
default value is 0. If it is 0, your 8051 is going to accept only level triggered signal. I am making that bit is 1 means it is going to accept edge triggered signal.
Yes, ma'am.
Okay.
I
This
have
set
a doubt.
set
But
that.
whether we should not require to check IT1 is 1 or not by clicking down of it.
Well, don't you do, here you can check your TCON register. There's no need of clicking IT not. You have to check the TCON register. So already that bit is set. Okay. So no need of clicking that particular value. So here it will shows only IT not alone, not IT1. So here we are using this program, we are using IT1. Okay. So that is not available in the simulator, Palaminakshi.
Yes, ma'am.
If suppose if we are using IT not, we can view the changes of your IT not bit here using this window. So this window supports only IT not and IE not IT1 and IE1. Okay.
Yes, ma'am. Actually, here we are not configuring it as input put, just we are
Just we are
fixing.
setting. Actually, that IT not at IT1 is a user defined bits. So using software programs, either we can set or clear the bit. Okay,
Yes,
the two bits IT not and IT1 is only as a programmable bit. So user can set and reset the bits in TCON register for edge triggering and level triggering configuration.
yes, ma'am.
Okay, in IT not ported when you can check this program using your KEIL interrupt system window.
Yes, ma'am.
Any other doubts? So please refer the Masudi books for reminding interrupts, okay? For your timer 1 interrupts, serial port interrupts. So embedded C and assembly program examples are, many examples are discussed in the Masudi. Please refer, and also if you have free time, you try this code in KEIL Microvision Simulator, okay? KEIL Microvision ID. Any doubts regarding interrupt programming? So next topic is serial communication. So serial communication in 1851. So first, before we start serial communication, 1851, we must understand some of the basics of serial communication. So we have two types of communication. That is two types of data transfer: serial data transfer and parallel data transfer. Okay, and serial data transfer is mainly used for long distance communication, and parallel data transfer is used for shorter distance communication, like IC, inside IC communication, or IC to IC communication, or motherboard communication. That is in motherboard inside your ICs. The ICs can communicate through this parallel data transfer. Okay, and what is the disadvantage of parallel data transfer? Any idea about it? Can you differentiate the advantages and disadvantages between serial and parallel data transfer? So parallel is expensive. Why it is expensive? So serial communication uses a single data line, but in case of parallel, we have 8-bit data line. So the parallel communication, parallel data transfer is expensive compared to the serial data transfer. Okay. So look at this diagram. So for a serial communication, the byte of data must be converted into serial bits using parallel in serial out. Okay, so the data is transferred to the another IC or destination or receiver through this parallel in serial out shift register via TXT line. Similarly, at the receiving end, we have serial in parallel out shift register for converting serial data into parallel data. And also, when this IC wants to transfer any data, okay, so that parallel data is converted into serial and transmitted via this line. And here we have serial in parallel out shift register. So for serial data communication, the byte of data must be converted into serial bits using parallel and serial out shift register. Then it can be transmitted over single data line. Okay, and also the receiving end, there must be serial in parallel out shift register to receive the serial data and pass them into byte. Okay, that is the logic involved in the serial communication. So, and before that, we have the two types of data communication: asynchronous data communication and synchronous data communication. So asynchronous method transfer a block of data at a time. So two types, synchronous and asynchronous. So synchronous means it will transfer block of data. While the asynchronous method transfers single byte of data at a time. So most of the microcontroller follows this asynchronous data communication. So your entire data byte is packed between start and stop bit. Okay. So asynchronous method transfers single byte at a time. So in this case, that is your serial communication. That is synchronous method and asynchronous methods can be implemented by writing programs, but the programming technique is very tedious and long. So for that reason, your 8051 has inbuilt UART, that is universal asynchronous receiver and transmitter. So there are special ICs made by many manufacturers for serial data communication to support asynchronous data communication. So your 8051 has inbuilt UART, that is universal asynchronous receiver transmitter, and another IC version is also available, USART. So this supports both synchronous and asynchronous way of communication. Universal synchronous asynchronous receiver transmitter. So coming into the basics of serial communication, we have three types. So serial communication is classified into three types of communication links: simplex, half duplex and full duplex. So simplex data line can transmit data only one direction. Okay. So the example, the data from sensors to processor. Sensors to processor or controller. It's an example of simplex data transfer. In half duplex, the communication links can be used for either transmission or reception. So data is transmitted in only one direction at a time. In full duplex, if the data is transmitted in both the ways at a time, it is a full duplex method, that is the transmission and reception can proceed simultaneously. So the communication link requires two wires for data, one for transmission and one for reception. So your 8051 supports both half duplex and full duplex communication. That is your serial port, 8051 serial port supports both half duplex and full duplex, and most of the applications we are focusing on full duplex serial communication. So this is the data format to be followed in your 8051 UART, that is universal asynchronous receiver transmitter. So here, when there is no data transfer means the signal is high, this is called mark. So this line is called mark, and your transmission starts with low signal. So this bit is called start bit, and LSB goes first up to MSB, D0 to D7, and finally one stop bit is in logic level high, again space. So this format to be followed during the serial communication of 8051. Starts your data byte 8-bit data was packed between start and stop bit. Okay. So for some cases, for error checking, the parity bit also included. So your 8-bit data start bit plus 8-bit data plus parity bit for error checking along with stop. So it takes 1 bit, 1, 8-bit, 1, 1. So it follows 10 or 11-bit format. Your UART follows 10 or 11-bit format. So 10-bit means it is 8-bit data was included with start and stop. 11-bit means your 8-bit data was included with start bit, parity bit and stop bit. And your data transfer rate is measured in terms of baud rate. So what is baud rate? What is baud rate? So the rate at which the bits are transmitted is called baud or transfer rate. Okay, please note it down. It's a very important parameter involved in serial communication. So the rate at which the bits are transmitted is called baud or transfer rate. It is a reciprocal of the time to send one bit. So the formula for this baud rate is 1 by T. One by T. It's a reciprocal of the time to send one bit. Suppose, for example, if the data is transmitted with 9600 baud rate, means 9600 bits are transmitted in 1 second. Suppose if the baud rate is 9600, which means that 9600 bits are transmitted in 1 second. Okay. So for 1 bit, your transmission time is equal to 1 second divided by 9600. So 0.104 milliseconds. So this is the transmission rate. Is that clear? The data transmitted with 9600 baud rate, it means that 9600 are transmitted in 1 second. So for 1 bit, the transmission time is equal to 1 second divided by 9600. So your transmission time is 0.104 millisecond. Okay. So this is the important, all your data transfer rate is measured in terms of baud rate. So the unit for the baud rate is bits per second. That is 1 by T. So next we will see about how to communicate 8051 to PC. So first point, to connect your TXT and RXT and RXT to TXT. So this is some of the basic points. So in order to follow your 8051 concept, suppose if 8051 is interfaced with PC, means it is connected through your RXT and TXT. So it can be interfaced with PC. The data can be transmitted and received via RXT and TXT, and your 8051 supports TTL logic level. So to convert the TTL logic level to RS-232 logic levels, we have to use MAX232 IC to transform the signal from TTL to RS-232 level, because your PC accepts only RS-232 level signal. Your microcontroller generates TTL level signal. So to convert TTL level to RS-232 level, we have to use MAX232 IC. And next thing, the baud rate, data transfer rate of IC, that is 8051, must match to the baud rate of your PC. Okay. So there are many types of baud rate, and in our applications we are using this 9600. So this baud rate is compatible with IBM PCs. So these 2 points are very important. I will talk that serial mode and timer in later sections. And your 8051 has internal UART circuit. So that internal UART divides the machine cycle by 32. So first, initially your oscillator frequency is divided by 12. So that value is again divided by 32 by your UART IC. That's inbuilt UART. So it's divide the frequency, mission cycle frequency by 32. And we have to use timer 1 in mode 2 for baud rate generation. I will explain that in the next class. Okay. So next class we will see about S buffer register. It's a very important register for serial communication. And next one is your SCON register, the serial control register. And third one is the PCON register. So there are 3 special function registers for mainly used for serial communication. One is SCON, S buffer, and PCON. So next class we will see about these special function registers. So any doubts regarding baud rates? So serial communication data rate is measured in terms of baud rate. Okay. So baud rate is, it's a modern terminology. It is measured in bits per second. That is 1 by T. So most of our 8051 applications we are using the baud rate value 9600. So in order to generate the baud rate, we have to use timer 1. Timer 1 in mode 2. That is auto reload mode. So any doubts regarding this? Students, any doubts? So next class I will explain S buffer register, SCON register and PCON register. Okay. Thank you.